Hello again. So I've had some boards drawn up for a while, been meaning to get through them. So I'd like to talk a bit more about complex conjugates and some of their uses. This is, by the way, kind of an addendum. There's a decent amount of algebra density here, but if you're not really for the algebra, it's also just nice to see what we can do with them. So, bunch of nice properties of the complex conjugate. Now, first of all, the definition. We're just flipping the I part, the sign of it, one way or the other. Visually, we have a number here. It has a length, it has an angle from the horizontal, and the conjugate is just going in the other direction. Which also, by the way, means that we can write it like this. We can write it as length times cosine plus I sine of the angle. And then z bar is the same thing, but with minus the angle because it's in the other direction. Incidentally, this also means that the absolute value of these are the same. Now, another nice property is if we add the number to its conjugate, then these cancel and we double up on the horizontal so that we have the z here, we have z conjugate here, we add them together and they converge at double the horizontal component. Similarly, if we subtract, then these cancel and these double up, and visually, here's z bar, and here's minus z bar. We add these two, and they double up on the vertical. Now, this is especially interesting when z has absolute value of 1, where z is just cosine plus I sine of some angle. So if we add these, that means that we're just doubling up on the horizontal, which is the cosine. And if we subtract, then we're doubling up on the vertical, which is I sine. And in the middle here, just a visual reminder that the absolute value is essentially, using the Pythagorean theorem. So horizontal component, vertical component, and the absolute value is given by the length. And it's just nice to note that we can also just multiply these two together and note that we're just squaring this and that these angles cancel out. So that's a nice way there. Previous video, did it by just multiplying through, same difference. Okay, and one last really nice property of complex conjugates is that if we like have any two complex numbers or circular numbers, because I don't really want to call them complex, see previous videos. But basically, complex conjugates works really, really nicely with arithmetic. If we want to take the complex conjugate of a sum, we just take the sum of the conjugates. Product, conjugate product, conjugates, divide, same, subtract, same, raised to a power n, that's just repeated multiplication, so same. And you can show this by expanding out either using this for adding and subtracting, or this for multiplying and dividing. But again, the real point here is just that the complex conjugate works really, really nicely with arithmetic. If you have an expression, you can generally just, and you want to take the conjugate of the whole thing, you can generally just take the conjugate of everything in the expression. Now, one consequence of this that you may have seen in an algebra class is, well, if you have a polynomial and all the coefficients are real, and then what that means is that if we take the complex conjugate of the entire polynomial, well, that just means all the things with a z in them instead of an x because complex numbers, but all the z's just get barred. That's it. So we just push this into all the z's. And what that means then is that the conjugate, p of z all bar, well, that's just p of z bar, like because it's just same z's, but they're all barred. What that means is that p of z is only 0 if and only if p of z bar is 0, because 0 bar is 0. But that only happens if p of z bar is 0, because p of z all bar is p of z bar. And let's see. And this, oh yeah, and this applies precisely because we're assuming that all of these are real. I should have probably mentioned that a little more explicitly because all of the coefficients, all the a's, well, real bar is just the same number. And again, don't like using real, so horizontal or regular or whatever. Okay, and this, but long story short, P of z is 0 if and only if P of z bar is 0. And that's why they always show up in conjugate pairs when the coefficients are real. Now, one application that's very useful and can use all of the properties is something called the law of cosines. And the law of cosines, from a previous video, is just that this thing squared is equal to this. And note that it has, the Pythagorean theorem piece, and then essentially an adjustment term. Now, to show that this is the case, we can start by, we can just assume A is just, horizontal only, and then B is just some absolute value times CIS of theta, which brings it this, gamma rather, which brings it this way. So, and then we can define C as, well, just A minus this. So this minus this. And C squared then is this times itself barred. Well, A is a real number. I know, okay, I keep reverting to that. And so, and B is not, not horizontal entirely. So the B has the bar on it. And if we multiply through by foiling, well, we have a BB bar here. Well, that's just B squared. And we have a AB bar and an AB, and we're subtracting both of them. So that's just A times the sum of these two. But hey, the sum of these two was just doubling up on the horizontal. And, well, the horizontal is just B times cosine of gamma. We're just taking the cosine out of the cosine I sine. And done. That's it. So again, if you want to go back and go slowly through it and just work out the algebra more for yourself, fine. But mostly it's just to show, one, that this squared is equal to this. So we have a general formula for the length of the remaining side. And it goes very quickly just by using all the all the basic arithmetic properties of the complex conjugate. So it's basically a speed run made possible by two-dimensional numbers. And incidentally, that also, it's like I was mentioning, that it comes in handy when we're trying to add the two spinning arrows. So if you watch the previous video, that'll make a little more sense. But, well, but yeah, that's about it. So more content later. Finally got that one out of the way. Bye now.